Welcome back. So for this video, I'm going to show you how to solve a system of linear equations using substitution. Pardon my paper shifting, I'm just trying to figure out the best way to lay this all out, so I've got it lined up on paper. So here we go. So there is another way that you can figure out the solution to a system of equations. One that does not need a table or a graph. It's called substitution. Now, remember, if you want to look at a table or a graph solution to a systems of equations, you can check out the video that I posted before this one called Intro to Systems of Equations, or I think maybe Review to Systems of Equations would be a better name for it. Anyway, let's go ahead and say that we had two equations like this, y equals x plus 1 and y equals 1/2 x plus 3. Now I want to figure out what the solution to these two equations are, or when do they cross on a graph, but I'm not going to graph them. So notice a couple of things. This is y equals mx plus b and y equals mx plus b. Because the equations are in slope-intercept form, they both equal y. As in x plus 1 is equal to y and 1/2 x plus 3 is equal to y. Because of this, we can write these two equations set equal to each other, like so. X plus 1 is equal to 1/2 x plus 3. Now, when I first learned this, I was very confused, but basically, if this is equal to y and this is equal to y, then they are essentially equal to each other. To help you understand this problem as an example, I'm going to tell you a story. Now, you have to kind of suspend your disbelief of accurate temperature in the Northwest, but go ahead and follow along anyway. Let's pretend for a second that the equation y equals x plus 1 is the temperature in Seattle for last February when we had that really big snowstorm. And then let's pretend that y equals 1/2 x plus 3 is Tacoma's temperature. Now, I know that the temperature probably only got around 30 degrees, but just go with me for this math problem. So let's pretend that Seattle's temperature, it was so cold in Seattle that it started out at 1 degree, and then every hour the degrees increased. As in, at 0 hours, it was 1 degree. At 1 hour past the time we started taking the temperature, so whenever we started was hour 0, and then after 1 hour, the temperature had gone up to another degree, 2 degrees. After 2 hours, it was up to 3 degrees. After 3 hours, it was up to 4. Now let's imagine at the same time in Tacoma, the temperature started out at 3 degrees Fahrenheit. I know, really cold. And then every hour, it's going up 1/2 of a degree. So that would look like this. At hour 0, the first hour we started measuring, the temperature was 3 degrees. After 1 hour's time, it had risen to 3.5. After 2 hours' time, it had risen to 4. After 3 hours' time, it was at 4.5 degrees. The systems of equations is asking us at what time or how many hours since I've started measuring will the degrees be the same in both cities. So that's what we're trying to figure out. So we're going to do this algebraically using x plus 1 is equal to 1/2 x plus 3. So we know how to isolate the variable. We did that last week. If you remember, before spring break, I had you guys practice equations with the variables on both sides. So here we have x plus 1 equals 1/2 x plus 3. And all I'm asking you to do here is just to isolate x so we can figure out what x is. And x is 1/2 of the ordered pair we need for the question of when will the temperatures be the same. In fact, x is at what hour, so how many hours have to pass before the temperatures are the same. So back to this, x plus 1 equals 1/2 x plus 3. Now, as we do in two-step equations or multi-step equations with variables on both sides, we just check and go through our checklist. Is there any distributive property? No. Do we need to combine any like terms? No. So now we need to isolate the variable by moving all numbers to one side and all variables to the other. I'm going to just go ahead and start here. I'm going to bring this 1 over to this side. This is plus 1, so I'm going to go ahead and subtract 1. I do that to one side, I must do it to the next. So x plus 1 equals 1/2 x plus 3. Subtract 1 from both the numbers, and I bring down the x. So this is just 1x. 1 minus 1 cancels, equals 1/2 x, brought that down. 3 minus 1 is 2. Now I have x equals 1/2 x plus 2. I need to get this 1/2 x over to this side And the way I can do that is using property of equality. So I'm going to subtract 1/2 x, subtract 1/2 x here. So I'm going to go through this. I have 1x minus 1/2 x, and look at the pink, not the purple. 1 minus half is half, equals 1/2 x minus 1/2 x is crossed out because it becomes 0. Bring down that 2, again in the pink. Now the purple is the next operation. I have 1/2 x equals 2, and I want to get x alone. What can I multiply by 1/2 to get x alone, or to make it 1? So I know that I can multiply anything by its reciprocal and make it 1, so I've chosen to multiply it by 2 over 1. 2 times 1 is 2, 1 times 2 is 2, giving me 2 over 2x here. I have to multiply this side by 2 over 1 because property of equality says whatever I do to one side, I must do to the other to keep it equal. So 2 times 2 is 4, and then my equation becomes 2 over 2x equals 4. We know anything divided by itself becomes 1, so this becomes 1/2 x equals 4, x equals 4. All right, so that means that we know, going back to this, that the ordered pair that's going to satisfy both of these equations is going to be when x is 4. So we got to figure out what is y. So it's going to be the next ordered pair down. So since we have x equals 4, now we just need to figure out y. All right, let's go back to the original equations. So I have y equals x plus 1 and y equals 1/2 x plus 3. Now that I have x equals 4, I can just plug x into either equation, the 4, and solve for y. Both equations work. I'm going to show you that by doing both. So here, instead of x, I've put 4, y equals 4 plus 1, and I do 4 plus 1 is 5, y equals 5. Now on this side, I plug in 4 instead of x also. 1/2 times 4 is going to be 2, and add that 3, y equals 5. So our ordered pair for the solution to this equation is, systems of equations, is 4, 5. So going back to my story problem, if x was 4, I'd put 4 plus 1 here, so this would be 4 or 5. I'm not going to write it because I'm holding the camera. And then over here for Tacoma, if x was 4, 1/2 times 4 would be 2, plus 3, y would equal 5. So 4, 5 would satisfy both equations, making both true, and that is when they would end up crossing. And I actually have, from my last video, if I can find it, the graph that I drew where they both cross. So there we go. The solution is 4, 5. All right, if you think you understand it, I want you to try and practice the problems that I've put out on today's webpage. And if you do not understand how to do those, feel free to watch the next video and I will go through each of them. All right, thank you.